context for anybody who's not a numerical relativist, the Weyl scalars are relativistic quantities which can be computed in a general relativistic spacetime, which describe how the curvature behaves, and specifically allows you to relate spacetime to gravitational radiation. So it's probably the primary way in which you can measure gravitational radiation in numerical relativity. So I guess this topic is a little bit mathematical, but don't worry, the talk won't be. So you have these Weyl scalars. So these are denoted psi 0 to psi 4. And I'll explain later how you compute them. But the central focus of the talk will be this peeling theorem. So this is a theorem from the 60s by Newman, Penrose, Sachs, etc., which says that under various general conditions, and these conditions are kind of important, how the Weyl scalars fall off with radius in a general spacetime that satisfies certain conditions. So the reason this is important is because of these scalars. Only psi 4 has a non-zero flux at future null infinity. And so this is identified with the radiative properties of the gravitational field. In other words, outgoing gravitational radiation. And this is why, from a physical point of view, this is very important. So the question that we wanted to answer is, there's this theorem which says how these scalars behave, and that psi 4 is the only one which has a non-zero flux and is identified with gravitational radiation. But we do numerical binary black hole simulations. And the question is, do the spacetimes that we compute, which are not exactly what you would expect astrophysically, but do the numerical spacetimes that we compute satisfy the conditions of the theorem? So we're not saying that we're going to prove this theorem or disprove this theorem. You can't prove a theorem with numerics. But we want to know whether you can apply the theorem to the numerical solutions that we have. So the types of initial data, the types of spacetime, can you expect that the conclusions of the theorem will hold? Because you can apply the theorem to the spacetime. The other issue is that when you say radius, you say that the theorem tells you how the Weyl scalars fall off with radius. What do you mean by radius? This is a coordinate-dependent thing. And the question is, are the coordinates that we use in our numerical simulations, which are built based on the solution, they're not fixed, they're not prescribed a priori, can we use these coordinates directly and call the radial coordinate that we use, can we call that the radius that you use with the peeling theorem? So in this work, what we did was we did a simple numerical binary black hole evolution, and we computed the scalars, psi 0 to psi 4, in some particular way, and we measured how they fell off with radius. So we basically tried to decide whether we saw the results of the theorem. And the summary is that we saw the results consistent with the theorem, and we conclude, therefore, that the spacetime and the coordinates are might be compatible with the assumptions. This is a kind of backwards argument that everything at least is consistent. And the conclusion would be that the methods that we currently use for gravitational radiation extraction in numerical relativity are supported well. So this might seem like a somewhat strange thing to do, given that it's a theorem and everyone would say, well, sure, of course numerical relativity, the spacetimes you use will satisfy the theorem. But there was this previous work a few years ago which saw something different. They saw that the psi 0 to psi 1 didn't fall off in the way that was expected, and people started to think, well, maybe there's something going on here, maybe there's a problem. But it turned out that there was actually an error in the analysis in the code that was used in that paper, and that was the major reason why there was this discrepancy. So we kind of wanted to, yeah.
Also, this guy who invariant Chrome, he also showed that basically, or you could just prove that boosted spinning black holes generally satisfy, I think, the standard peeling theory, as we know. So it predicts other Falloff waves.
Yeah, so there may well be cases which don't satisfy the conditions of the theorem. And I know.
This is surprising to me that even such simple
Is it that it doesn't satisfy it, or it can't be proved to satisfy it?
I think it was, I'm not totally sure, but I think it was a strong statement.
Okay.
He said that it's not, he showed that it's not true.
So it wasn't completely crazy to think that maybe there was something wrong, because there are examples. Okay, so what are these Weyl scalars I keep on talking about? So you have 5 complex scalars. So this is 10 scalar fields, 10 real scalar fields, which measure the curvature of the spacetime. So these are computed by contracting the Weyl curvature tensor with this complex null tetrad, which is made up of L, N, M, and M bar, which are defined in some sense. So it doesn't really, I guess they have to satisfy certain conditions, but in our case, we take them to be L as an outgoing radial vector, N as an incoming radial vector, so radial null. And these are some sort of angular combination. So, of course, what you mean by ingoing and outgoing is, I'll come to later. So you contract the Weyl tensor with these different tetrad components, and this is psi0, this is psi1, psi2, etc. And you have physical interpretations for each of these. So, for example, psi2 is sort of the Schwarzschild Coulomb part of the field, so it just decays in some simple way if you have Schwarzschild. It sort of describes the mass that's in the system. And the interesting one usually is psi4, which is the outgoing transverse radiation. So that's the gravitational radiation that you would detect with a gravitational wave detector, which is LIGO or something. So this is how you compute these. So once you've got these, what's the Peeling theorem? So the main result, due to Sachs, Newman, and Penrose, is that for a given psi, so we had psi0 to psi4, let's say psi n, should fall off as r to the n minus 5, so this is a power law, near scri plus, so near future null infinity, on outgoing radial null geodesics. So this is not a fall off in just spatial directions. It's important that you're going along null geodesics. And the theorem is a statement about what happens in the neighborhood of scri plus. So I drew a picture here. So this is the sort of the world line of a binary black hole simulation. So you have an in-spiral and a merger. So time goes up, radius goes out, and you have outgoing null geodesics. This is kind of just a cartoon, although it was built from real data. So you have the in-spiral signal here, the merger signal here, ring down signal here. So this is psi4. And if you trace along outgoing null geodesics like this, you'll see some feature, maybe this peak here, and you'll see that it gets smaller. And this is the fall-off that we're measuring. So the fall-off along these null geodesics as a function of radius. And here are the fall-offs that are expected for the different components. So psi4 is 1 over r, and that's why you get a non-zero flux at scri plus. Psi0 is 1 over r to the 5, and it decays very, very rapidly. So there are various conditions, mathematical conditions at scri plus, which must be satisfied in order to prove this fall-off, this theorem. And basically none of these conditions are things which we can check numerically. So the definition of the radius, for example, the radial coordinate that we're talking about here when we say r, is defined with respect to some conformal transformation at scri plus. We don't even have scri plus on our grid. So we cannot directly verify these conditions. The other important thing is that these tetrad vectors, the n and l, which I said were ingoing and outgoing, should be aligned with the radial null directions. And these would be outgoing and ingoing at scri plus. And we don't, as I said, we don't have scri plus on our grid. So those are not things which we can compute directly. Now in numerical relativity, so I said that you can construct psi0 to psi4 by taking a tetrad and contracting it with a curvature tensor, the R tensor. So how do you choose this tetrad? So on the previous slide, I talked about some conditions on the tetrad when you want to apply the Peeling theorem, which are defined in terms of mathematical properties of scri plus. Numerically, we can't do that. We don't have that on the grid. So what we do is we take our coordinate basis vectors. These are dynamical coordinates that evolve during the simulation. And we make some sort of sensible choice that we think, as you approach future null infinity, will approach the correct thing. And from these coordinate vectors, we form a null tetrad, which in fact is null. It's not approximate to null, it actually is null from the unit hypersurface normal. And so this gives us the tetrad that we then contract with the Weyl tensor in order to compute the scalars. So the issue is, how does this tetrad behave as you approach Sky Plus? Does it satisfy the conditions that would allow you to apply the peeling theorem? Is the coordinate, the radial coordinate that we use in the simulation, which is dynamical and maybe asymptotically is what you would expect to be the right thing, but is that compatible with the theorem? Can we use the usual techniques of numerical relativity to demonstrate the peeling theorem? So in order to compute the scalars, this is more of an applied slide, we use a code called Weyl Scalars 4. And this computes psi0 to psi4 during the simulation. So this is not just an analysis, this is during the simulation, in the Cactus framework. This was written by Tanya, who we have in the audience here, and myself while we were at Penn State. The code is generated automatically. So the code to compute these, the expressions, is lots of contractions with Riemann tensors and tetrad vectors with lots of indices. It's kind of complicated. So we use automatic code generation, and this code is freely available. So if you want to use it, go to einsteintoolkit.org, find the code, download it, check it, and use it. So for this project, we used a multi-patch code called Llama, and we wanted to use this crank-generated code, Weyl Scalars 4 with Llama, so we needed to make sure that that worked. So we enabled that, tested it, so that's all working now. And then we checked that Weyl Scalars 4 was correct by cross-checking it against another code, an earlier code, and against some analytic results for the I invariant in Kerr. So I'll talk a bit more about that later. But we spent quite a lot of time testing and debugging this because of the problems we had with the previous result, and we found that there was some bug. And it took a long time to figure out what that bug was. And so we were quite careful to check this as thoroughly as we could, because we didn't want to make any mistakes. Okay, so the test case that we were using was a black hole binary. So maybe, what are we now, 2011? 6, 7 years ago, people couldn't do this. But nowadays, it's pretty easy. So all the codes that you need to perform these sorts of simulations are now freely available, open source. If you've got a big enough computer, you can run them. And you can do binary black hole simulations in numerical relativity. So this is the coordinate tracks. So the binary starts at a separation of about 6 in units of the mass of the black hole. You get a nice little circular orbit. And this is the waveform that you get. So this is measured at, I don't know, I can't remember what radius. So this is the 2-2 mode of the gravitational wave. So you have the junk radiation, in spiral, merger, bring down. It's a very simple test case. It's 1 or 2 orbits. We didn't need a very long simulation for this because really we just need to show how does the radiation decay. It doesn't really matter what the signal is. So what do the scalars look like? So this is for the different scalars. So here's psi4, psi3, psi2, psi1, psi0. And this is the extent to which we could measure them. So we measured them at r equals 40 along the x-axis, I think. And this is what they look like. So you can see this is a little different from, for those of you who've seen waveforms before, it looks a little different than what you would expect if you were doing a mode decomposition, because this is measured at a point. So it's not exactly what you would see if you did a mode decomposition. Anyway, so this is what the scalars look like at a point as a function of time. And if you look at the scale, you can see psi4 already has the largest amplitude, psi2 is a lower amplitude, and psi0 is very weak indeed. And as you can see, there's a lot of noise. This is just numerical noise. So the features of it are correct, but there's a lot of noise on top of it. This is because the signal is very weak in comparison to the other parts of the solution. So I said that when you investigate peeling, you're supposed to look along outgoing null geodesics. So we don't calculate the geodesics numerically. We could do. There's nothing that would prevent us from doing that. It's a little bit awkward, because in order to calculate the geodesics, you basically solve some sort of ordinary differential equation for the geodesics. And you want the ones which are radial, but you want the ones which are radial at large distances. So you can't just start with something radial, because it probably won't remain radial. So for that reason, it's a little bit awkward to calculate these numerically. So what we did was we said, well, let's just, the first guess is that a null geodesics, assume our t and r coordinates are reasonable. And so everything travels at the speed of light. And for large distances, this is fine. So for a long way away from the source, these coordinates are pretty realistic, and you get reasonable measurements using this. We also tried, the problem is that for small coordinate distances, when you're very close, the coordinates are very dynamical. This is not, the speed of light is not 1 in these coordinates. The coordinates simply don't reflect the null GD6. So we also tried something which might have been a better approximation, which was to use a tortoise coordinate. And this was a little better, but it wasn't sufficient. What we did do is we said, well, we don't know where the GDX are because we haven't computed them. We can't use one of these simple approximations, so let's use something different. So we assumed that psi4, which is the gravitational radiation, that the peaks of psi4 propagate along null GD6, which is a reasonable assumption. Although I think mathematically it's not a rigorous statement. And then we defined an approximate null GD6 as some curve which is the path traced by one of the peaks of psi4 along the x-axis. So we were assuming that the GD6 along the x-axis remained along the x-axis. This is another approximation. So here we have an approximation which is probably the first approximation that we bring into the system. And this seemed to work pretty well. So here, I guess I'm showing the outgoing. Yeah, so this is along the x-axis. So this is, you can imagine the wave is propagating in directions of positive x. So the first thing that comes out is the junk radiation as the initial data settles down. And then you've got some sort of in-spiral oscillation, merger, and then a ring down. And we numbered the peaks. So each of these peaks corresponds to a number GD6. So I've said lambda I is one of the curves, one of the GD6. And you have these different ones. So I think most of our results that I show are from this one because it was relatively strong and hadn't been contaminated by reflections. So what happens? So this is a plot of the scalars and radius and time. So this sort of radius time axis corresponds to one of the GD6, so lambda 1 in this case. And you can see that the amplitude of psi4, for example, decays. This is on a log plot. As it goes out along this curve, this approximate GD6 as a power law. So this is a log-log plot, so it should be a straight line if it's a power law. The dashed lines are the best fit straight line, and the colored lines are the numerical data. The fitting is performed between these vertical lines. So for psi4, psi3, and psi2, we fitted in this region, which went out to something like r equals 1,000. And for psi1 and psi0, which are much weaker, we had a lot of difficulty with these. So the problem is that because these decay so quickly, you can see several orders of magnitude weaker than the other ones. What happens is that we get numerical reflections which contaminate this behavior. So when you're very close, you can see that it's a power law decay. But when you're far out, you start to get noise. So you can see a little bit of noise there. And it's actually this particular way of representing it doesn't show as much noise as there really is in the signal. But anyway, so what conclusion do we draw? So if we do this fitting, we can measure the fall-off rate. And for each of the scalars, psi0 to psi4, this is the expected rate, 5, 4, 3, 2, 1, and this is what we measure. So for, we basically, within the error bars, so the error in the last digit is in parentheses here, for psi0, approximately for psi1, and then when we get to psi2, psi3, and psi4, which are the ones at large radius, the estimated error bars, which come from finite differencing error, actually don't cover the errors that the difference from the expected result that we're seeing. But we're pretty certain that this is due to the fact that we're fitting at a finite radius. So the peeling theorem says that you get a certain fall-off rate, but only if you do this at future null infinity. And seeing as we don't have future null infinity, we have to fit at a finite radius. And we've checked, and as you move the fitting region, this number gets closer and closer to the number that you expect. I've got a plot about that if you want to see it. So another thing we looked at was what we call curvature zones. And this is, in some sense, just a cartoon idea, because take it as a qualitative idea. So this is, we defined a zone. So the first thing we defined was psi k, which is the modulus. Now I'm getting confused. Right, we defined psi as the sum of the psi's, or the sum of the modulus of the psi's. So we can then take a fraction, we can say how much does psi4 contribute to the total gravitational field? This is not some useful quantity that you would use for anything, it's just a rough idea of how much, what's the relative strength of each component. So psi4 is close to 1 as you go to larger and larger radius. So as you go to larger and larger radius, psi4 completely dominates all the others. All the others fall off much more quickly. As you come in from infinity, you start to see that psi3, which is the green one, gets stronger and stronger and stronger. And what we did was we defined these zones. So we said zone 4 is the place where psi4 dominates. Zone 3 is the place where psi3 starts to be more than 5% of this total psi. And the same for psi2, psi1, psi0, which is actually beyond this block. So this splits the space-time into separate zones, where you could say that this was some sort of radiation zone, and then other zones for where the other components become important. So there's a big caveat with this, which is that if you change the geodesic you look at, or change some criteria like the 5%, which we just chose arbitrarily, you will get a different picture quantitatively, but qualitatively you still have these different zones. Now, as I said, we had some technical problems with psi0 and psi1. So psi0 and psi1 fall off very fast with radius, distance from the source. And by r equals approximately 70, they have very low amplitude. Now, I said we were using this Llama multi-patch infrastructure, which allows us to go very far, have our grid extend a long way from the source using angular coordinates. And this allows us to very accurately measure the fall-off of psi4, psi3, and psi2. The problem is that the way it works is you have this angular patches, and then a Cartesian patch in which we do traditional adaptive mesh refinement. And the interpatch boundary causes lots of reflections. So we have features in the solution at the beginning of the simulation which propagate out. They have quite high frequency. They reflect off the interpatch boundary, and they come back, and they start to contaminate what we can see. And in order to get psi0 and psi1 accurately enough to measure the fall-off, we couldn't actually use this setup. So we're actually using a different simulation for measuring the weaker psis. What we did was we used a Cartesian simulation with a very far outer boundary, as far away as we could afford numerically. And then we were able to see, so then we just ran the simulation until these psi0 and psi1 were contaminated by noise. And then we were able to measure the fall-off accurately. So we also, just a technical detail for anyone who knows about these things, we still couldn't get the accuracy we needed until we used a numerical technique called tapered grids. This is to do with the way the mesh refinement works. And this is, in fact, the first time I've seen tapered grids give a significant improvement to a numerical result. Okay, so I guess that's the end of the physics portion of the talk, but seeing as this talk is part of the Cactus and Einstein Toolkit workshop, I thought I would talk a little bit about correctness testing in Cactus and the Einstein Toolkit, because it's kind of relevant for this, and a lot of the work that we did as part of this project was related to correctness testing. So I would say that doing scientific software, writing scientific software, the correctness testing is difficult and it is a lot of work. Unfortunately, we can't really get away from it. What we need to do is we need to find a way to make it easier. And we need powerful and convenient analysis tools in order to do this. I think when simulations were run on maybe people's workstations, they were small scale, codes were simple, maybe correctness testing wasn't so important. It was obvious if your code was right or wrong. Now we have big collaborative codes, many contributions, codes which maybe have been around for 10, 15 years. I think having correctness tests is a very important thing. We don't have anything. So the code that we use is based on this Einstein toolkit. And we don't have any formal correctness testing in the Einstein toolkit. We only have regression testing. So we know that if somebody makes a change to the code, we know whether the results are the same as they were before, but we don't know if they're correct or not. The correctness testing is manual. It usually happens only once, and it is rarely documented. We have many components which make up these codes. People test them when they first write them, and then that's it. You have to trust the original developer. Maybe there's a paper where they describe the tests that they did, but quite often there isn't. There's no easy way to verify the correctness of the code. And sometimes correctness testing doesn't happen at all. So if part of the code isn't used for something, maybe it's not even tested. And as a user of the code, you don't know whether that's the case or not. So I just had a proposal, which is that we could have a formal correctness testing framework for Cactus in the Einstein toolkit. This would be similar to the existing regression tests that we have. It would be easy to run by users in an automated way with no thought. So you just run a script and it says, I'm going to test that this is correct. There would be a pass or fail for each test. And the description would be stored as part of each module. So the idea would be that this is different to the test suites that we currently have, in that it tests the physics correctness, not just that the results are the same as before. This is something that could take longer or more memory, or even require a cluster, in comparison to the regression tests, which have to be run quickly. So Weyl Scale 4, which is the code that we were using for computing the scalars, as part of this project, we tested carefully that this was correct. So when it was originally written, Tanya and I tested it extensively, but we didn't test it against an exact solution. We tested it against an existing code. And this was fine, and that's why we were confident that it was right. Of course, it's better to test it against an exact solution. So we tested this as part of this project. We cross-checked it, again, against the old code, which is how it was developed originally, using Mathematica. And we checked it against exact results. We were able to produce 2D contour plots of rescaled errors to show the convergence to the exact solution. So usually you look at convergence maybe of norms, or maybe in 1D. If you have good enough tools, which we have with Mathematica, you can do more advanced convergence testing, for example in 2D, to show visual convergence in contours. This was something that I quite liked. So the test against the exact solution we did, so this is a contour plot, this is the xz plane. I'm plotting this I invariant, which is a combination of the scalars, which is supposed to be independent of the tetrad. So this combination in Weyl-Lindquist coordinates, this is the analytic solution. And we're showing the blue and the red. So the blue is the numerical solution, and the red is the exact solution, just on one slice of curve data. And the contours line up with each other. I haven't put contour labels on, but you can see that they line up. This is another code, which is the one that was used in the original project, the one which got the wrong results. And eventually, after a lot of work in developing this infrastructure for comparing these things, we discovered that there was obviously something wrong. The numerical and the exact solutions just didn't agree with each other. And this helped us to track down what the problem was. So that's an analysis code. What about evolution codes? So evolution codes can be tested against exact solutions to the Einstein equation. So now I'm talking about Einstein evolution codes. So for example, there's a shifted gauge wave exact solution. So this is Minkowski space with a non-trivial coordinate transformation, so that when you evolve it numerically, it becomes, it's not just, it's non-trivial. So what we've done is we have a testing framework which does a convergence test against exact solutions, and we've applied it to 4 different numerical codes which solve the Einstein equations. These are all in the Cactus framework. Given that you could have subtle errors in the implementation, you generally need several different tests. You may find that you do one test and the code passes it because you haven't exercised part of it. So for example, if you did an unshifted gauge wave, maybe there would be an error in the shift terms. I mean, maybe the shifted gauge wave is a strong enough test to be fairly confident in the code, but it would be good to have more than one test. So something that we've been doing at the AI is working on a database of metrics in Mathematica. So at the moment, we only have a small handful of metrics. But these are expressions which can be used for various purposes. So if you're doing relativity calculations, maybe you want to have some metrics available, and there is not currently such a database. When I say database, I mean a directory full of Mathematica source files. It's not really a database. And you can download the work in progress here. We want to test that these metrics satisfy the Einstein equations. If you're going to use these in numerical relativity, you want some assurance that they're correct. And you can test that using some computer algebra package. For example, we use xtensor, which seems to be the leading Mathematica tensor manipulation package. So you can compute these are vacuum metrics, or you can compute the Ricci tensor and show that it's 0 for these metrics. So then, now that we have a representation, a mathematical representation of the metrics, we can actually generate code from these. So we have this code generation package called crank, and we've written something which takes this metric of database. It does a 3+1 decomposition, which is what you need in order to do a numerical evolution. And it computes initial data thorns, initial data modules in Cactus for all of the metrics, any metric in this database. And we have a Cactus arrangement called Einstein exact, which has these thorns in it. So we would like this at some point to be added to the Einstein toolkit. We think this would be a useful thing to have. This would be more accurate than things which are currently used. And you would have the advantage of formal verifiability of correctness versus the handwritten code that is currently used for exact solutions in the Einstein toolkit, with which we have found problems. So there are errors in there are known errors in the way that the extrinsic curvature is calculated. Small errors, but still, it's better not to have them. And actual mistakes in some of the metrics that actually make them wrong. So as an example of the metrics database, this is the description of the shifted gauge wave metric. So half of this is just a comment saying where it comes from. It comes from this paper. These equation numbers. There's a few little definitions. It's called shifted gauge wave. This is a description. And this is a Mathematica representation of the metric. So from this description, we can generate an entire code which will set up the initial data within Cactus, which can then be used for testing of evolution codes. So in summary, I guess my talk was in two parts. So I talked about the work that we did to calculate the Weyl scalars for a binary black hole spacetime, psi0 to psi4. This needed a careful treatment in terms of the numerical grid structure for psi0 and psi1. Technical reasons, reflections, we needed to work quite hard to get those accurately. We defined a concept of approximate null geodesics, which corresponded to the way that peaks in the radiation propagated outwards in the grid. And we measured the fall-off of these scalars along those null geodesics, approximate null geodesics. We obtained rates consistent with the peeling theorem, which was reassuring. And then we defined some sort of qualitative curvature zones to describe which was the dominant Weyl scalar in different parts of the space-time. So just in general, as a summary, this gives us confidence that the standard interpretation of psi4 as gravitational waves using standard numerical relativity techniques, the ones that we use now, is justified. And as a little rant that I guess I was having at the end, is the correctness testing is hard. It is very difficult with these complicated codes. And that I propose that we need formal, reproducible correctness tests and powerful analysis tools to avoid mistakes. Thank you. So I omitted some details on that. So the initial data was Kerr in Kerr-Schild coordinates, whereas the expression I gave for the I invariant was in Boyer-Lindquist coordinates. So the testing of the Weyl scalar was just done in Kerr. So we didn't test it for the binary, because we wouldn't know what it would be. Mm-hmm. So would you need a whole binary for that, or just a
Just a
boosted spinning black hole?
But for a binary, it would manifest itself, I guess, a large way if you have a kink in the system, right? You have asymmetry variation, and this might affect.
Yeah. Okay. Yeah. We looked in the z direction as well. So the z direction in general would be preferable because we had an equal mass system which has a rotating pi symmetry, which means that by the symmetry of the system, we know that any geodesic along the z-axis remains along the z-axis because it's the symmetry axis of the system. So it would have been preferable to use that because then we would have known that we had most of the components of the geodesic correct just by symmetry arguments. The problem with that is that I think the imaginary part, what was the problem? I think the symmetry also means that one of the components, the psi4 is 0 or something. I can't remember the exact details, it was a while ago. So we had some problem. Do you remember, Ella? No, why we didn't use the z-axis. Oh, right, because the tetrad is singular there. Yes, okay, so that was the reason we didn't do it. So we didn't test along any other directions. So only psi4. Sorry, only the x-axis. Yes. So we on the Falloff, right? Right. So what we did say was, well, so the thing we were most concerned about was along the x-axis, the geodesic may not have been radial. So we were assuming that the geodesic would remain along the x-axis. And we worked out, we did a back-of-the-envelope calculation in Kerr and found that to very high accuracy at the distances that we were using, if the solution was Kerr, which it isn't obviously, but assuming that it was, that you wouldn't get any sort of dragging effects beyond like, I don't know, 10 to the minus 5 radians or something. So we considered that to be a very good approximation, that the geodesic would remain along the x-axis. But as for angular dependence of the fall-off rate, I think we could measure it in some cases along the z-axis, and we got reasonable results. So I think we thought about that, and I think there was some technical issue with it, which is that it's not.
I mean, for a wide tensor, you think you always have this, for space, you always have this most four, right? They're completely different, or they coincide. The measure of what kind of heterotype you are is how close they are to each other. I mean, ideally, if they, for example, if they're all the same, then you're on heterotype n. There's only one principal measure. You could measure how close they are to a different type.
But at any point, we will always have 4 distinct ones, because at no point are we in any of those Petrov types, except for the most generic.
I mean, if you're Petrov type n, square plus, then you have to have principal directions that all coincide.
Yes, and this is something that perhaps could be checked by somebody who had ready access and experience with a null code.
You can do that everywhere. For example, Kerr, which Petrov type was there?
D.
Yeah. Okay. But there, I think you have two principal directions which are not coinciding. So the pair of two principal directions. For instance, there
But I mean, this is not interesting. It's
But
just,
it relates to the Falloff, because you can measure at larger radii how the principal null directions actually peel off. I mean, you start from null infinity. Okay, you don't have access to that, but on the Cauchy domain. But as you move closer to the source, you should see how the principal null directions peel off.
so you would measure something like the angle between the eigenvectors, I guess. Yeah. Okay. So I think we did discuss it, and there were two reasons. I think one is that it would be very complicated and difficult. You have to solve an algebraic equation at every point. Maybe this is expensive.
You also have to figure out you have to transform the Bondi gauge before you find the correct coordinates.
But the other thing is that I seem to remember that there was a problem with you need some sort of background, and you don't know what that background is. I can't remember. But I remember when we discussed this that we decided it wasn't feasible to do.
Yeah, it's probably, measuring some. Yeah, I understand that. It's the obvious way to go. Look at the side points. I was just wondering.
Yeah, we tried to shortcut as much as possible. This was the minimum we could get away.
I think it would be very interesting to actually see the principal null directions peel off.
So in some sense, this is related to the zones thing. So when psi4 is dominant, the thing is that the peel off is always going to be, okay, so you have some angle that it peels off at. How do you interpret this as just some number?
Yeah,
And
that's right.
it's difficult to know. You could do all this work and then you get a number and you don't really know what the number means. But maybe there's something interesting in it. Yes, we did. So, so this was something. So I think this might be something which doesn't show up in Kerr. Because the tests we did were with Kerr, and then afterwards, like much later, like only a few months ago, somebody contacted me and said, we're trying to use psychedelia. What's the issue? And I said, yeah, there's this issue of them being flipped over, and we never saw it during the testing. So obviously our correctness testing was maybe not rigorous enough. Sorry? I think the psi0 and psi4 would have shown up in the same way in that test.
I think it's just a flip in the upper and in the null direction.
Yeah, which is what it is.
Yeah.
Yeah, it's a convention that nobody else ever uses. Right, I think. Psi4 would be 0 if you were in the right coordinates, which we were not. So in Boyer-Lindquist coordinates, you would have only psi2. But what we were looking at was Kersheld coordinates. And so we actually had to do the transformation of the analytic solution from Boyer-Lindquist to Kersheld, and then that's what I was showing there.
So the correctness testing was just not complete.
I think yes. So it was yeah. So when I did other tests afterwards, I did find this discrepancy to find that they were flipped.
You say you should make correctness testing easier.
Yeah.
But how would you like that easy automated differentiable correctness testing against it in situations like a binary technology where it's not ever?
In that case, you can't. But I think at least having some sort of correctness test of each individual component. I mean, even if it's just that the constraints converge or something, like whatever the minimum, whatever you can do in each case, I think you should do. Because at the moment we have absolutely nothing. We just trust that the original developer was right. Or we set up a test case, which is already a lot of work, and then run it, and check it, and debug it, and write the analysis, and everybody is expected to do this on their own, or trust the original developer. And I think with these large collaborative scientific software platforms, we need to have something like this. Of course, finding the manpower, and it's a thankless task, right, this sort of thing. But I think it's important. T equals 0, slice. So the other infrastructure that we have for doing these exact solutions is this exact module, and this allows you to do funky slicings through the data. So we've added. No, so we realized that this was not, we were not providing that feature. So what we did was we allowed, I think, rotations, and we could allow boosts. But we figured that if somebody wanted another coordinate system, you can just use that, code that coordinate system up, or make the transformation in Mathematica, and then make that a new metric. We didn't want to. The problem with doing the coordinate transformation is you do the coordinate transformation numerically, and this introduces another approximation. And so we decided that that sort of thing should be done analytically in Mathematica, and then the numerical code should be created. Otherwise, you have additional sources of error which you have to take account of. No. So if you wanted Minkowski, you could select Minkowski, or you could select gauge wave, or you could select shifted gauge wave. So it treats them as separate metrics, the ones in the different coordinate systems. And if you wanted to do a coordinate transformation, I would do that at the level of Mathematica, not at the numerical level, because it's not necessary to do it at the numerical level. Yeah. Right. Oh, I see. So you have some automate. Yeah, okay. That's a good idea. Yeah, we'll think about that. More questions? Well, we could always have rotated the tetrad. So the tetrad is well defined along the x-axis. We could have simply rotated it or defined it in different ways so that it was okay along the z-axis, I guess. But one subtlety which is sort of difficult to appreciate is that a lot of what you're testing is the property of the tetrad. So we wanted to show that the tetrad that we were using was the correct one, or has the right properties, has the right fall-off in some sense. So if we change the tetrad, it sort of muddles things up a little. So the reason the tetrad is not defined on the z-axis is because it's one of the components of the tetrad is based on a spatial vector, which is something like dd theta. So it's a polar vector. And so once you sort of come up to the axis, it's not defined anymore. What direction would it be in? And of course, you could make some different convention, or you could use Cartesian coordinates. And then, yes, I guess you could measure the fall-off of the new scalars with the new tetrad along the z-axis. I don't know how interesting that would be, though. Maybe because of the symmetry argument, yeah, that might have been a better thing to do. I don't think so. I mean, in principle, it doesn't have to. If you go close enough, where's the plot? So we had. So the term is. Yes. It's not the dominating one, no. Sorry, I might have said that. That's not correct. So yes, it's where you contribute more than 5% to the total. So in fact, psi4 is not the dominant one when you get very close. And sort of in the limit, which isn't included, this is log scale. It's not, the limit is not included. You get psi0 being the dominant one. No. new intuition. The tetrad is in some sense spherical, so you wouldn't get an effect from that. The space-time itself, I guess, has some sort of deformation related to the fact that you have two separated black holes. Where it starts to become important. I don't know. Yeah. Yeah, you could also just divide the two scalars. So there's probably more direct ways of showing that. I mean, we output these things, we can output these things in 3D and have a look at them. So we could visualize that, I think. Yes. All of these, the scalars all depend on the tetrad. That's why we used an invariant as for the correctness tests. So the E and B are the E and B that are used to construct the scalars? If it's the E and the B that are used to construct the scalars, then it's the electric and magnetic parts of the Weyl tensor. Yeah. So we use a direct Riemann decomposition, but the other form, the one that was used in the old work, Cyclops, does both decompositions, and so there you have explicitly the E and the B fields. So that should not be difficult. So you can talk to Dennis Polny, who's the author of that thon. There could be. I think it would be easy to add, yes. It's quite different. Yeah, you could do that, but it would be much easier to use Dennis's thon because those things are already explicitly in the code. You just have to output them. Mm-hmm. Yeah. Mm-hmm. Yeah. Yeah. Thank you.